So first off, do we think this is an endo or an exothermic reaction? Exo. How do I know it's exo? Because delta H is negative. That's how I know. Now, if it was written in the equation, it'd be plus 1204 on the right-hand side. Okay? But because it's a negative delta H, I know that it's an exothermic reaction. So now I need to calculate the amount of heat transferred when 3.55 grams of magnesium reacts at constant pressure. And the only thing we can say at constant pressure, that just means I can calculate delta H. I can do everything kind of the same way. We always are going to assume constant pressure. We're never going to calculate heat at any other conditions. So, what do I start with then on B? 3.55 grams. And that's magnesium. Okay, so then what do I have to do? Molar mass. 1 mole over 24.3 grams. Okay, so that tells me how many moles of magnesium I have, something less than a mole. Then what? Negative 1204 kilojoules for every 2 moles of magnesium. And again, that 2 is this 2 right there. Okay? So it's always going to be, when you see the delta H, it's kilojoules per however many moles that are reacting. So you always have to divide by whatever the coefficient is. And all of that turns out to equal negative 87.9. And it's just going to be kilojoules because moles cancel. So when you're looking for calculate the amount of heat, that's just going to end up being kilojoules when you're given a quantity, because we know. That's kilojoules per 3.55 grams of magnesium that's burned. So if I wanted to go kilojoules per gram, what would be the only thing I'd have to do? This is kilojoules per 3.55 grams. If I divide by 3.55, I can get how many kilojoules per gram. All right, so C. How many grams of MgO are produced during an enthalpy change of negative 243 kilojoules? This is just going to be in the reverse. You always start with the given, find the appropriate conversion factors and set your units up so they cancel. So negative 243 kilojoules. Well, what's the only conversion factor that has kilojoules in it?
It's 234.
234. What's the only conversion factor that's got kilojoules? The 1204, right? So it's going to be, this time it's going to be 2 moles of magnesium every 1204 kilojoules. So that tells me how many moles of magnesium it's going to take to produce this much energy. Okay? Notice it's going to be a fraction. So now, but the question wants to know how many grams of MgO. Okay? And again, it's 2 moles of MgO, so this is 2 moles of MgO. And it would be whatever the coefficient is on this one, because the question's asking about this one, so we look for the coefficient on this one. Times what? Molar mass of MgO, which is going to be 24.3 plus 16 makes 40.3 grams over 1 mole. So moles cancel, that's leaving me grams of MgO, which is how much?
15.7.
Okay? 15.7 grams of MgO. So in other words, when magnesium reacts and makes 15.7 grams of MgO, you can expect to have this much energy released. So notice it's just a stoichiometry problem. It's just setting the units up and using kilojoules per mole as a conversion factor to go between heat and moles. Everything always goes through moles. And then lastly, D, how many kilojoules are absorbed when 40.3 grams of magnesium oxide is decomposed. So in other words, we're just going to do the reverse reaction. The reverse reaction is just going to mean that plus 1204 is going to be over here. We're going to be going right to left. That makes it endothermic. This is the reaction that occurs naturally. We have to force this one to happen by adding heat. And so when we look at that then, we're going to do the exact same thing. It's just going to be positive when 40.3 grams of MgO. So we just go, start with the 40.3 grams MgO. What do I do? Molar mass of MgO, which we already know to be 40.3. Okay, so that means it's how much? It's 1 mole. Okay, well, how much energy is needed for 2 moles? 1204. So we know it's really just going to be half of that, but we can just say positive 1204 kilojoules over 2 moles MgO. So that's just going to be 1204 divided by 2, which is equal to 602 kilojoules. So you just have to add in that much heat. Okay? So stoichiometry problems are really very straightforward. You just always have to remember, if you know the heat of the reaction, that's a conversion factor between kilojoules and moles. Okay, we all good with this? All right, that's the first way of measuring enthalpy.
Is that the easiest way?
Do what?
Is that the easiest way?
Yeah. Well, actually, none of them are hard. It's just the hard part of thermo is recognizing what type of problem it is and what equation you're going to have to use, because they all kind of use different equations. Now, the second type is calorimetry. So what do you think calorimetry is a measure of?
Calories.
Calories. Okay, now if you go through the notes, we've already covered most of what they talk about in calorimetry. It shows the coffee cup calorimeter, defines heat capacity and specific heat capacity. It defines Q equals MCAT, okay? And so this is always going to be Q lost is equal to negative Q gain. Q lost is equal to negative Q gain. So, but all we have to do on these is we have to look at, if we look at this coffee cup calorimeter problem, this sample problem here, get it just right. Okay? When we want to look at this problem, it says in a coffee cup calorimeter. So again, that's just your markers. That's just going to be a beaker with a styrofoam cup, coffee cup in it. And you're going to do the whole reaction in here. This is all just air in between, but trapped air is a great insulator. I don't know if have you ever heard of an insulated window? At your house, they have some insulated window. Well, you don't see pink stuff in between the windows to insulate. What they do is they just have an air gap. They have 2 panes with an air gap in between, and that air gap is a lousy conductor of heat, and so it insulates, so there's not as much heat gets from the first window pane to the second window pane. Sometimes there's super expensive ones, you have 3 layers. You got two, you got 3 pieces of glass with 2 air gaps in between. The pink stuff in your attic, the pink stuff itself is not what's the insulator. It's the trapped air within that pink stuff that's the insulator. And so that's always going to be the best way to do that. All right. Let's go ahead and take a break. And then we'll come back and we'll look at doing some of these problems.